This is lecture 1.11. In this lecture, we are going to look at block diagram reduction. So we have already seen in the last lecture some complicated transfer functions, especially the one related to the DC motor, which had a number of blocks. So to find out the transfer function of such a system, you would require to combine those blocks together and to get the transfer function in the form so that you could process it further. So today we are going to see how to do that block diagram reduction in case you have a multiple subsystem system, that is a multiple subsystem system, a system which has many subsystems. How do you combine the various blocks to get a simplified representation which you can use and process for further analysis? So before we begin this, let us go through some of the terminology that we have already seen. These are these arrows represent signals. So we call them signals because they are normally voltages, currents, pressures, so on and so forth, forces, velocities, and they are basically processed by the systems on which they are acting. So these are called signals, right? This is the general notation and the general terminology. Then you already know that you have a system in block diagram form like this. So RS is normally your input, and it gets processed in the through the system, and you get the output. And a notation like this means that your output is actually equal to RS into GS, where RS is the signal and GS is the transfer function of the system. So when you draw something like this, it automatically implies that CS is equal to RS into GS. Then you have the summing junction. We have also seen this. So you have three signals here entering. One is entering with plus sign R1, the other R2 with plus sign, and the third is being subtracted. And the signal at the output is CS. It is going to be the sum of R1 and R2, and you have to subtract R3. So R1S plus R2S minus R3S. Please remember that we are drawing everything in the S domain. So that is why everything is a function of S. Then you also have something called the Pickoff point. This is important. So if you have the signal RS somewhere and you want to distribute it, then you can just pick it up from here and you can distribute it the way you want. For example, in this case, RS is being picked up and you're dividing it into three parts. Basically, it is not division. It is not like, current dividing. You can think of it like tapping a voltage, right? So it is like RS is a voltage here available for you to tap, and you're tapping this voltage and you're taking it to three different sources. So please remember that when you have a Pickoff point, your signals don't get divided, they remain the same, right? This is important because this will stop many confusions from occurring in the future. So what kind of systems do you have? One simple example could be of a cascaded system. A cascaded system has a number of these blocks in cascade, right, or series. So you have G1S, G2S, G3S in cascade. And if you have something like this together, the overall transfer function is going to be the product of the three. And why is that? It is because, very simply, if this is RS and this is CS, and your intermediate signals you want to label X2 and X1, then X2S would be G1S into RS, because this RS is entering G1 and getting processed. And then G1S into RS would be multiplied with G2S. So your other intermediate signal would be G2S into G1S into RS. And then again, this is getting multiplied with G3S. So the third signal is going to be G3S, G2S, G1S into RS. So basically your CS is going to be G3, G2, G1, S into RS. And if you want to represent this as a single block, you can write down CS by RS is going to be G3, G2, G1, which you have done here. So Cs by Rs, the transfer function is G3s into G2s by into Gs. So remember that if there are systems in cascade, then you just multiply them together. Similarly, if you have systems in parallel, you add them, right? And again, it is very simple. If you have Rs, it is being fed to three systems, G1, G2, G3. You have this intermediate signal Rs into G1, this intermediate signal Rs into G2, and this intermediate signal Rs into G3, and you're adding them up because these three are in parallel. You get Cs is equal to G1 plus minus, depending upon what is the sign, G2 plus minus G3 into Rs. So it is actually Cs is this times Rs. That means Cs by Rs would be G1 G2 plus G1 plus G2 plus G3 in case all these signs are plus, and in case any sign is minus, then correspondingly that entry would be minus. That is your IE, you have plus minus plus minus plus minus. So basically, if three systems are in parallel, you can very easily derive this thing and say that the transfer functions just get added up, right? The third important uh, uh, the third important form in which these systems occur is in the feedback form. In the feedback form, you have a diagram like this, where you have Rs and Cs as the output, Rs as the input, Cs as the output, and then the output, you have a feedback path, and the output gets multiplied with the sensor, and this sensing network has a transfer function given by Hs, and then you add or subtract it to the input, right? So you have something like this. Now, how do you find out the transfer function for this? Again, it's not very difficult. It's very simple. In fact, the simplest thing. So what you can do is try to find out what is this signal. Now, this is a Pickoff point. So if this is Cs, this is going to be Cs, right? And if this is Cs, what we can do is we can write down this as Cs into Hs, right? And then what is happening is that you're subtracting this Cs into Hs from Rs. So this Es that you're having here is Rs minus Cs into Hs, right? And then this Es gets multiplied with Gs to give you the output signal, which is Cs. So from this relationship, you can write down the relationship between Cs and Rs. So if you want to simplify this further, I can write down Rs into Gs is equal to Cs plus Cs into Hs into Gs, right? And I can write down Rs into Gs is equal to Cs 1 plus GSHs. And you can write down Cs by Rs is Gs divided by 1 plus GSHs. So this is the transfer function for the feedback, negative feedback. So I have taken this as negative. That is why I have Rs minus Cs. In case this is negative, is feedback is the most common feedback. In case it is not negative, it is positive, then you have a minus sign here, right? So that is why you have in the feedback path, the overall transfer function is G divided by 1 plus minus GH. If it is negative feedback, it is 1 plus GH. If it is positive feedback, it is 1 minus GH. So these are three most common categories, right? And now if you have a complicated block diagram, what are the strategies that you use to simplify it before you're able to write down the transfer function in a compact notation? So one strategy is called is moving a block to the left or to the right of from a summing junction. So sometimes you need to do this, and we'll see soon why we need to do this. So say you have something like this, right? You have a structure like this, and you want to move this summing junction to the right of the block, right? So what is basically what is basically the output CS here in this block. If you see the output CS, it is going to be RS, and let us take the plus sign, for example, just the plus sign. It is going to be RS plus XS, right? That is the signal that you have here into GS, right? So this is what you want. What is CS? Now, if you move it past the GS block, right? So what you need to do is, see, RS has to be multiplied with GS, and XS also has to be multiplied with GS, and then you have to add the two up to get CS. So you again see CS here. This 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 signal here is RS into GS, and this signal here is XS into GS, and you're adding the two up to get CS. So your CS is again RS plus XS into GS, right? So in this case, CS is RS into GS plus XS into GS, which is equal to RS plus XS into GS, right? Which is the same as what you got earlier. So in case you have to move the summing block, right? In case you have to move the summing block to the right of the junction, you have to move it like this. And in case by the equivalent treatment, you can also see that if you want to move the summing block to the left of the junction, then you have to actually do like this. So sorry, like this. So the summing block is already to the right of the summing junction is already to the right of the block, and you want to move it to the left. What you do is you divide it by GS, because here your CSC, again, if you write down your CS, it is going to be RG. If I drop the subscript S for brevity, it is going to be RG plus X. And again, if you see your C here, your C is going to be, what is the signal here? It is going to be R plus X by G, right? Because this G is getting divided. And then you're multiplying this R plus X by G with G. So what you're getting here, C is R plus X by G into G, which is R G plus X. So you're getting the same thing that you actually wanted, right? So this is if you want to move your summing block to the left or to the right of if you want to move your block to the left of a summing junction or the right of the summing junction, right? And then you can also do a little bit of manipulation for Pickoff points. For example, you have something like this in this case, and you want to convert it. You can convert it to something like this, where you're basically moving this block to the left of the Pickoff point. So this block is to the right of this Pickoff point, right? And you want to move it to the left of the Pickoff point. So you do something like this, right? Move to the left of the Pickoff point. And since you have multiplied this RS with GS to get the RS signals here, you have to divide it. So you do it like this. In a similar way, if you want to move the block to the right past the Pickoff point, then what you can do is you can take this RS and move the Pickoff point to the right, but you have to multiply each Pickoff point with GS. It's very simple, and I don't think it needs a lot of explanation. Let's get to an example where we're applying these techniques. Suppose you have something like this, right? You want to solve this. Now, how do you solve this? Do you need to do any manipulations in this? You don't need to do much in this, because you already have. So what we want from this problem is to have a block diagram in this form, final form, where the RS is the input that is entering the system, CS is the output from the system, and you have this overall transfer function. So how, from observation, we can see very clearly that these two are in cascade. So you can multiply these two and say this is G2, G3. And then this G2, G3 and H1 are in feedback. So this whole block here can be replaced by the overall transfer function, which is basically negative feedback. And for negative feedback, you have G divided by 1 plus GH, the overall transfer function. So your G is G2, G3, and your H is H1. I have dropped the subscript S for the bracketed term S for brevity, but you have to write it. So your overall block, which is colored in green here, will be G1 G2 G3 divided by 1 plus G2 G3 into H1. And then this big block is again has a feedback, right? So this is your big block here, and this again has a feedback which is H2, right? And what you can do, this is positive feedback. What you can do, you can either write down this as, again, simplify this from your knowledge of the equivalent transfer function for a feedback block, or if you want to do it in one step, you can do another thing. You can combine these three blocks. These three are in cascade. These three are not in cascade, sorry, they are in parallel, right? So you can combine these three are in parallel, and you can combine these two, they are in a cascade, right? So one way to do it is to write it as a number of feedback transfer functions, right? The first one I've written for you, then this is in feedback with H2, and then that would have H3 in feedback, right? The other way, which is the shorter way, would be to write down, let me do that, would be to write down G2 G3 together as a single block, right? So you have this G2, sorry, you have this, let me write it down here. So you have this G2 G3 combined together, G2 G3, right? And you have this G1 out here, and these three can be combined because these are in cascade, these are in parallel, and H1 is negative, H3 is negative feedback, but H2 is positive. So this is a feedback path, all three of them. So minus H1 plus H2 minus H3, right? And this is all that you're taking from CS, right? And then these three are, you have added the three together, right? So you have taken care of the negative sign by taking H1 as negative, H3 as negative, and that's why you have a positive sign here. So you can equivalently, from this complicated diagram, you can move to this diagram in one step, right? And the next thing that you're going to do is to write down the expression for this feedback loop. The expression for this feedback loop is going to be G divided by 1 plus GH, and in this case it's going to be 1 minus GH because it's positive feedback. So minus H1 plus H2 minus H3, and this whole block, right, has this transfer function, and this gets combined with G1 because G1 is in cascade to it. So this overall, you can write down CS by RS is equal to this much, right? And you can simplify this. So in another step, you have done this, and in the third step, you can slightly simplify this and remove this negative sign here and write down this as G1, G2, G3, 1 plus G2, G3. Take this minus sign inside and write down H1 minus H2 plus H3. This is the overall transfer function for this problem, right? So this is what has been done in this also. So you have G2, G3 here, and you have this. He has taken this as negative feedback, so it doesn't have a minus for H1 and a minus for H3. He has a minus for H2, and in the end, the result is the same, right? Okay, so now let us take another problem. So this is a slightly more complicated example in which you have a number of blocks and a number of summing junctions. Obviously, you cannot simplify this without manipulations. Why? Because suppose you want to simplify this thing that you have here. The problem is that if you simplify this feedback loop, because this is a feedback loop, you have G2 in the forward path, H2 in the reverse path. If you write down the feed transfer function for this whole thing, you will lose this signal V3, because you have then V2 as the input and V4 as the output, and this intermediate signal V3 is lost in between because you're picking up from between. So you need to do some manipulation and simplify this before you're able to actually apply your knowledge of block diagram reduction. So what do we do to simplify this? Now what we can do is the first thing that is very obvious is that you move this Pickoff point away. Don't pick V3 because you want to simplify this, right? You want to simplify this block. So don't pick V3, pick up V4. And if you move this V3 and this Pickoff point here, what you are picking up, this V4 is actually V3. Sorry, it's actually V3 into G2. So if you're picking up V4 instead of V3, then you'll have to divide it with G2. And this V3 G2 that you're picking up from here, you'll get V3 exactly if you divide it by G2. So this is what you're going to do. You're going to take this Pickoff point and remove it from the block diagram, because this is going to help you in simplifying this. So this thing would be removed and you have just picked it up from this point. So this is what the book tells us. If you look at the solved example, so the first thing that he does is that he moves the Pickoff point outside. And now what you do, the next thing is that you can combine. So you're picking up V4. So whether you have this V4 here or you have this V4 here, it's one and the same thing, just picking up V4. So you have two blocks in forward paths, right? These are in parallel. One is 1 by G2 and the other has a gain of 1. So this block has a gain of 1. So what you can do is these two are in parallel. You can combine the two of them together. So you have the next manipulation that you do is that you combine this 1 by G2 plus 1 together. These